So I'm going to talk about 2D parametricity. So first off, the talk will be about parametricity. I thought I'd give a basic introduction to it in my own eyes, because that's what I think about it. And then I'll go to the second half and talk about what 2D parametricity is. So when I was thinking about this talk, I was reading the question and I noticed this paragraph in the introduction. It's full of work on three theorems, like population parametricity, of uniformity, logic, sound patterns, underlines, Rex, John, Sharp, with the information all of which is to say two things. First of all, parametricity is a really interesting thing, but it's weird because not everyone really knows about it. So hopefully part of this talk is telling you about it. And the second part is, as in a lot of fields, well, inside parametricity you see two things. You see some really beautiful mathematics and some really good applications to fields that are real pioneers who actually extracted from that mathematics the really good PL ideas. So let's talk about this topic. Right. So parametricity is not about system math, although it's often studied in the setting of system math. It is called the numerical calculus called parametricity. So what does it contain? There are various types which you can form. There are type variables, very simple. There are function types, and there are universal quantity types. And that's all there is. It's a remarkably simple calculus. And also, one of the amazing things about it is it's remarkably powerful. Of course, to ask you to study with us before we turn, I'm not really going to talk about this one. Now, normally when you are given a calculus, you try and find some sort of model of it. This is what I do, and so you might imagine, if you've got a type which has some three type variables, if I give you, some sets of the type variables, I'll give you a set, like list of x. If I give you a set for x, then I can get a list of them. So in parametricity, we do something else on top of that. We augment it. That's sort of standard set theoretic views and that with another one. And what does it say? It says, well, imagine I've got two environments, two collection of sets to replace all the type variables. And imagine that I have a relation between each of those sets. So it calls a relation between the environments. Then, what I can produce is a new relation. And this new relation is the action of the type on the first collection of sets, the first about, and the action of type on the second collection of sets. So, for example, R is a relation between x and y. The list of x is it's a type, a non-free type variable. The O is the map sets of sets. So we'll take a relation and create a new relation, Mr. R. And what is this relation between? It's between Mr. X and Mr. Y. So you just do normal semantics, but you lift it, you add on a semantics to do with relations, a relational semantics. So, I must admit, as I get older, the length of the formulas I can parse gets smaller. So this is about the longest formula I can parse these days. So for that reason, we're going to switch to diagrams. So, this is what some parametric semantics will look like. We take a type, and yes, as we said, we get a map which takes an environment of sets to set. We can also get another interpretation which takes relations to relations. And then the fact is that it's just a relation between some types, some sets. Then the relational interpretation of the type on that relation gives you a new relation between the sets computed by the standard. Okay. One thing I think is worth pointing out is when I realised why parametricity is really good is because this doesn't just tackle those type expressions that are covariant. This also deals with contravariant type expressions. But these are remarkably hard and included in a very fertile area for research over the years. The Catholic theorists have wandered down sort of dynatural routes and strong dynatural routes. But I would say one of the great things about parametricity is it's the right answer to dealing with mixed variance. You can tell, because these type forms, you notice the domains of discrete categories. They don't act on morphisms. Okay. So, what else do we do in parametricity? I'd say that's what we do with types. I should tell you what happens with terms as well. So imagine we've got the judgment of this form. So in some context, we have a term type T, where we also have some term variables. Well, this is a type, so we have its standard semantics, and we have relational semantics for it. A delta, this context of term variables, of course, it's just a collection of types being applied. So already, it also has a standard semantics and a relational semantics, and their terms just correspond to lateral transformations like that. And then finally, the last thing we want to do with parametricity is, well, this relational transformer takes relations to relations, but what happens when given input a collection of equality relations? So that's some sets, I work equality relation out for them, so that, and then I apply my relational transformer to them. Well, I get a relation a priori, who knows what I get. But actually, it's key to prove what's called the identity extension level, which says that I get the same relation as I apply equality to standard semantics on the input sets. So that's the key of parametricity. Now you know what parametricity is all about. It's about taking the standard semantics of types, augmenting it with the relational semantics, doing the same thing for terms, and proving the identity extension level. If you want a snappy slogan, we're not going to terms of types in terms of functors and lateral transformations, but prime functors and prime lateral transformations. Yeah, on this, on this. And I'm afraid I'm not 10 foot tall, but T1 on top of T0 plus T0. Okay, so that's the goal. This interpretation of types and terms and proving the identity extension level. And we're going to do this, apply that program, the system F in this talk. So in order to get these semantics, that T0 and T1 that I was talking about, we have to use structural induction on the different type formers. So there are only 3 type formers, so it's not a priori too difficult a project. If you've got a type variable and some sets for all the different type variables, or the ith type variable, set, we've got a relational environment, and a type variable with straight line elements. Obvious? Now let's have a look at what we do with function types. Well, if you do a function type and you want to know what it does in a collection of sets, well, it just returns a function space. So you convey the person, you encode the person. So syntactic function space is interpreted as a normal function space. But now comes the interesting part. We have to give a relational interpretation to this function type. So what do we do? Well, I'm going to tell you when 2 functions are related. So this is what the relation we get. It says that these functions F and G are related. Whenever you have 2 inputs that are related, then you apply the function to the first input and the second function to the second input, they'll be related. So this is building in into our definitions the idea of parametricity that things map related inputs to related outputs. That's a slogan here over and over again, and that's in essence building in preservation of relations, relatedness into definitions. So the relational semantics allows us to talk about that. Functions are related, which means to be related, and that related inputs to related outputs. Okay, where are we now? So that was type variables, that was function types. All I've got left to do is tell you what we do with raw types. Okay, so this is what I do. We're going to calculate this set, the interpretation of raw x of t, when I've got an environment theta for all the different 3 type variables. Well, what do I get? I always wondered when I make a podcast. Right, so this is going to get set, and intuitively we know what it should be. It should be the set of polymorphic functions. So it should consist of, guess what? Polymorphic functions. You give me any set of input, and I'll give you a appropriate value inside this set. But if I just stop here, I could just have random functions. If S was bool, do something. If S was int, do something. If S was something else, whatever you like. You know, a nice set theoretic graph, nothing more. But we don't want that. We want to capture this uniformity. So we're only going to take these ad hoc polymorphic functions. We're only going to keep them if they satisfy uniformity criteria. In that sense, where relations to A, B, we apply X to A and X to B and X to Y, they must be related. If you like, you can think of this as say that A and B are related, so you get related infrastructure. That's the central stone, the central concrete stone of that chunky system. Okay, so that's the second polymorphic functions. But of course, also when two polymorphic functions are related, well, guess what? Same sort of thing again. So for any relation between A and B, then the first polymorphic function is like A, and the second polymorphic function is like B. They must be related to the appropriate relation. So this is called the logical relations, and they define those semantics, well, T0 and delta 0, that we use to then prove these properties. Okay, so that's my brief tour of parametricity. So the key thing in parametricity is really, first of all, getting these logical relations down, defined, and then proving these sorts of theorems. Now what I want to do, so that's the introduction, what I want to do in the second half of the talk is talk about two-dimensional parametricity. So in order to do this, I'm going to give some motivation. And now I'm going to solely focus on this. Put this down. Right. So what I've done is I've just copied down what we had for the function space before. So we've got two relations, R and R prime is a relation between function spaces, and two functions are related. For every pair of inputs, they're related in the inputs, then f applied to x and g applied to y are related in the R prime. Now what I want to ask you is, what happens if we listen to the type theorists in the room? What happens if we listen to the constructivists in the room? And what happens if we listen to the active programmers in the room? Which I do most of my life, and it's a very rewarding experience. But what they tell me is actually, so far, we've been taking a relation between A and B to be a subset between A times B. And they tell me, I believe they tell me, they usually tell me, that they don't want to do that. What they really want is to say, no, 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 no. What they would like is to take their relations to be set valued. They take their predicates to be set valued, take their relations to be set valued. Because what you really want is for any A and any B not to know if they're related. You need a witness for it, you need a proof for it. They want the set of proofs that these things are related. So the goal of this work is to see what happens to relational parametricity when we try to take our relations to be set valued relations rather than propositions. Okay, so here we are. We have to change our logical relations, and then we have to prove those properties. I'm not going to prove the properties, I'm going to talk about the logical relations. And this is one for Aaron. So that's fine. We've changed our notion of relations, but we still want to form this exponential relation. The question is, what happens here? Well, I learned quite a long time ago that when you start doing set valued things, you replace quantifiers by arrows. So let's try and do that. So what we might write is something like R arrow R prime. So I want to know when F and G are related in R arrow R prime. But of course now, this thing will be a set. So what set is it? Well, it's roughly this set. Except, of course, I can't write for all x, y. What I need to do is have a function. So it's a set of functions which say, given an x and x, y and y, x, y, r prime, fx. G1. Okay, so not so hard. Everything's going fine, I think. Let's carry on. What we need to do next, let's get rid of this piece of paper, is look at the logical relation for all time. How is this going to change? Well, the first line, we need an ad hoc polymorphic function. That's fine. But now again, previously we had a predicate. We need to turn that into a function. And so we might say, let's not have that. Let's rather have call that f0. Let's have a function called f1. So this takes any relation between a and b and gives me a proof that fa and fb are related in the appropriate relation. So again, just turning predicates into arrows. So far, everything's fine. Very good. Are we going to get lucky with this line? Well, now of course we need to say the relational interpretation of this type. If you give it a relational environment, when will f and g be related? Oh, but now we don't have an f and a g because an element of this polymorphic type with an f0 and an f1. So in fact, I have to say when an f0 and an f1 is related to a g0 and a g1. And what should I write? I'll write the obvious thing. Well, it should be a set. It's a set of functions. So it's a function to take a relation tape of a relation to a proof that f0 applied to A and g0 applied to B are related. And I think, phew, I'm done. That wasn't very hard. Because I've transferred everything, all the predicates, and turned it into function spaces. And I sit down and I congratulate myself and I think, oh, which conference shall I have an exciting venue I can go to? And then you do the proofs and you realize, oh no, this is a disaster, this doesn't work at all. So let me explain some of the things that go wrong. Well, first of all, we're studying parametricity. We want to prove the identity extension lemma. So what we'd like to do is, that involves cutting things down. We took f0 and in order to be parametric, we cut it down so that it's uniform. But this f1, this is just an ad hoc polymorphic function. There's nothing uniform about that. That causes the problems. Similarly, we've introduced these functions here, which construct relationless proofs. We've said nothing about how our f1s are going to interact with these ones as well. So the problem is that when we use predicates, we're talking proofs about uniformity or ad hoc. That's fine. There is no structure. But when we're in a proof-relevant world, there is structure. We can't use ad hoc polymorphic functions at the proof level. They must be parametric as well. So how are we going to do that? We need to add a 0 level, which we made parametric by adding a 1 level. How do we make the 1 level parametric? I know. We added 2 level to constrain the 1 level behavior. So the 1 level behavior will be parametric in the same way that the 1 level constrains the 0 level to be parametric. So, therefore, we have to introduce, if you want to construct this exercise and we want to do the identity extension lemma, we're going to have to introduce 2-dimensional relations to constrain and to make the 1-dimensional proofs parametric. Yeah. Right. So, what is a 2 relation? Well, we have some guidance. So if A and B are types, we say relation to A and B form a type, and this is what the definition is. So what are we going to do with the 2 relations? We can quite much the same thing now. We can say R is a relation between A and B, and R prime is a relation between A prime and B prime. Then we'll have the type of 2 relation between this relation and that relation. And that's fine. And that sounds appropriate. And what should a 2 relation be? Well, I'm going to start turning to writing more and more diagrams because, as you'll see, the syntax of these high-dimensional relations gets very long. And I've already told you I'm getting quite old. So this is a relation These are two relations. What's the two relations between this relation and that relation? The natural thing to do is to think, oh, I know what I could do is do that. So a two relation between the relation R and the relation R prime is a Q with all these maps. That seems entirely plausible. And then every two relation has two associated one relations, and you can also see how to embed a relation into a two relation. And so this relationship between well and set gets replicated here. Oh, lovely, this is looking nice. Let me tell you what one of these two relations is in concrete terms. Well, what it says is so a two relation, you want to write out in typographic terms according to this definition, says whenever you've got any pair of base elements, for relations we just took any A and B, well, so any four tuple, we know that A and B are related, and A prime and B, A prime and B prime are related. So we've got two proofs, we can give a set of proofs that those are related. So that's what a two relation is according to this definition. So does that work? Well, how much time, Sam? Okay. Choice time. Well, that doesn't really work. And I'll give you a flavour of why that doesn't work. Why it's the wrong definition. So, we use some categorical analysis to try and avoid writing down those big sigma formulas and pi formulas to work with simple diagrams. And that idea of taking two relations and then they span over their roots, I can write them down like this. I mean, there's just R. There's F, I'll write them differently, but there's Q between the two, between the R and the R prime. So I've just changed the geometry slightly. And you can see that it's a little bit odd, because in some sense, the A and the A prime are sort of dangling, unassociated with each other. And the B and the B prime are dangling, unassociated with each other. And that bites you in certain proofs. Another way of looking at it is concretely, if I took my polymorphic function, applied it to a relation, then F1 of R will relate two values, G1 of R5 will relate two values. But these two values at the bottom and the two values at the top, they remain unrelated. So I've unconstrained everything. Parametricity is about uniformity, it's about squashing down the amount of stuff that behaves very well. And I've not done enough of that. So bad category theory, gave me the wrong answer. So what I want to do next is just tell you what the actual definition we came up with is. And the one that actually works. So I guess I should, it's worth saying that we were sitting being frustrated in our office that our definition, the previous one, didn't work. And then Bob wandered in and said, have you thought about this? And then this turns out to be the right one. I think it goes back a lot further. We've seen it in papers by Marco Grandis on various different things. So it's quite an old definition, but it is exactly what we need for this very computer science idea. So what I want to do is not just consider a relation between an A and a B and another relation here between a C and a D. I also want to have relations between the two bits at the bottom and the two bits at the top. So I've got a square of relations. So whereas previously a two relation was over two relations, now a two relation is over a square of relations. That allows me to form the type. And what is a two relation? Well, the two relation says, again, take 4 points from the corners, and then if the if A and C are related, so take 4 tuples of proofs to prove that your A and your C is related, A and B is related, a B and a D is related, a C and a D is related. I choose some of them. So when all these like four tuples of proofs going to be related. So that's what we've got there. Another way of looking at them is the following. Let's see if I can fill this diagram in. R0. There's some very complicated notation that I'm struggling to remember every time I do this. No, that's a sign that there's something complicated about the subject. The subject is very combinatorial. And you see if the technical metaphor, that's just a two relation. Of course, we're going to do this in omega relations, so it's going to get even more complicated. It's just the combinatorial. I mean, this is better because it's some kind of naming scheme. But that's what two relation is. If you see, it's just what we had before, minus these things. So I stuck a relation here, a relation here, and I made these a relation. So that's what a two relation is. And now, whenever I write the stars are reminders for me that I need to write something. Right. Okay. So one thing I wrote here, Cartesian connections. When you look at these notions, remember when you had set, the relation, you had two sets that it's between, and you had one equality which turns relations into sets. With these two relations, actually the structure gets much more complex. Clearly a two relation has four relations it's over, and there's more than one equality, i.e. there's more than one way of turning a relation into a two relation. And these things are called degeneracies. And there's also things called connections. I don't want to go into that, but all of you young, very, very clever, hot people will understand what I'm talking about. Okay, so leaves me out too, that's why I left it out. Sometimes one just has to pass them off. Right. But actually, when you said previously, does that mean it's bad notation? I defended it, but actually there's better notation that comes along. So in fact, actually, we can write set. I mean, set is just the category of functors from 1 to set. Obviously. And rel, that's just the category of functors from the span category. That's 3 objects and 2 non-identity morphisms into set. But you'll just get sets replaced in the vertices. Okay, so what about 2rel? Well, I just told you that that is this category, functors from there to set. You know, that's getting quite complicated. But actually, when you look at this, this is actually just the same thing as this category cross itself into set. And in general, n relations are just I can tell you what an n relation is. It's just an n-fold product of the span category into set. Or even better, if I define rel C to be functors from the span category into C, then I can say n plus 1 rel is rel into n rel. Relations inside, sorry, that's a bit low. N plus 1 relations are just relations internal to n relations. So you've got a very beautiful recursive structure that will hopefully contain the combinatorial complexity of writing all those things down. If you want to, write down what a 3 relation is in type theory. I mean, just write it all down here for every A, for every B. It's a very long formula. And then what you notice is that when you start doing all of this, as I said, you don't just have, you have face maps, you have degeneracies, you have connections. You actually end up using all the kind of algebraic structure that you find in cubical type theory that all the very clever young hot people are doing. So although I started off with just this idea of taking parametricity and making it proof relevant, which forced me to add an extra layer of parametricity, when I worked out what that extra layer looked like algebraically, I realized we're at the lower levels of the cubical categories. So I think that's quite exciting, really. It's like, you know, the homotopy type theory are doing their structure for their reasons, but the same thing turns up in this setting. I think that's quite, I mean, either that's curiously deep and interesting, or it's a massive red herring. Okay. So If you want to now finish off the rest of this talk, go and read the paper. You'll see the logical relations written out using these two relations. My main goal to tell you today was what a two relation is. And I hope I've told you in such a way that you also know what an n relation is. And here are my conclusions. So, I think this higher parametricity arises naturally if you want to study proof of parametricity. You write down your set valued relations, you realize you don't have the uniformity, you have to put a second layer on, you naturally iterate, you have higher dimensional parametricity. It's sort of not an option if you want to go down that route. If you take your proofs seriously and you want uniformity. I mean, I am a category theorist, as most of you know, so I would say this, but it's a very clear case where the combinatorial explosion of all these face maps of degeneracies make it hard to write down in type theory. It makes it easier to write down in category theory. I guess what we'd really like is then to find a type theory that's based upon the category theory that hides that combinatorial complexity. And I believe people like Torsten and Bob and various people are working on that. And finally, the moral of the story is that structure I first told you, globular stuff, that's bad, cubical stuff, that's good, and there's definitely this hot convergence. So, thank you very much for your time.